MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll work a problem on hypothesis testing involving two population means, but this time the population standard deviations will not be known for either one of them. So the problem setting we have is the following. A new bumper is installed on selected vehicles in a corporate fleet. During a one-year test period, 12 vehicles with the new bumper were involved in accidents with a mean damage of $1,101 with a standard deviation of 696. Notice that this 696 is a sample standard deviation. We do not know the population standard deviation. During this same year, 9 vehicles with the old bumpers were involved in accidents, incurring a mean damage of $1,766 with a standard deviation of 838. Did the new bumper significantly reduce damage? And we have to use a 5% level of significance. Again, 5% means that I'm willing to accept a 5% chance of making the wrong call, that is rejecting the null when in fact it's true. We are controlling for type 1 errors only. Notice that the two populations that we are comparing here, one is set of cars with new bumpers, the second population is set of cars with the old bumpers. Just to ease the notation, I will use the subscript L to represent old cars, the old population, and the second population will be represented by the subscript N, meaning new bumpers. Okay. So the first step in the hypothesis testing problem, of course, is to set up the two hypotheses. We'll follow our guideline, that is, whatever claim it is we are trying to establish or test, we would like that to be the result of rejection of the null. So in this case, the claim that I'm trying to test is that the average damage with the new bumpers is less than the average damage with the old bumpers. Then that would be the case if the new bumper significantly reduced damage. Therefore, my alternate hypothesis would be mu n, that is the average damage with the new bumpers, would be less than mu old. And notice that I've set it up as the alternate because that being the claim that I want to test, I want that claim to result, if I do go with the claim, I want that to be the result of rejection of the null. That's why it's been set as the alternate. Once the alternate is set up, whatever is left over is the null hypothesis, which in this case would be mu n greater than or equal to mu l. Alright. So there we have the null and the alternate, and as you know from the previous problem that we worked, this can be rewritten in the following manner: mu n minus mu l is less than 0, just shifting the two variables around, and the null would be mu n minus mu l greater than or equal to 0. So there we have our null and alternate hypothesis. Clearly then, the way we would choose between the two is to see what our samples tell us. So the sample statistic that I would use to make this inference is obviously x bar n minus x bar l. So what does the sample tell us? The sample tells us, the sample data that we have is listed on the right hand side over here, you can see. So the sample tells us that x bar n minus x bar l is minus $665. So it does appear, in fact, that the new bumpers are producing less damage on average than the old bumpers. But of course, we won't know if this difference of $665 is large enough for us to say, yes, this is quite extreme, it didn't occur by chance, until we standardize this number and see how far is far indeed. Okay. Since we do not know the population standard deviations, since we have to use the sample standard deviations, you know from prior exercises in confidence intervals and hypothesis testing that the sampling distribution of the sample statistic, so the distribution of x bar n minus x bar l, will be a t distribution, not a normal distribution. With every t distribution you have degrees of freedom. In this case, the calculation for the degrees of freedom is rather messy. You remember this formula that we had gone over in class. So I've just written the formula over here. It's not a difficult calculation, but a tedious one. And you will end up with degrees of freedom equal to 15.4, which has to be rounded up to 16. So for our problem here, the sample statistic that we are going to use, namely x bar n minus x bar l, has a t-distribution with 16 degrees of freedom. Okay, and what is the standard deviation of this t-distribution here? So sigma of x bar n minus x bar l is given by square root of sigma. Instead of sigma squared over n, you have s squared over n. You just substituted the sample variance instead of the population variance. So you have s squared n divided by the sample size of the new cars, and then s squared l divided by n of l. You work the math out, it comes out to $344. So that is the standard deviation of x bar n minus x bar l. Now we are in a position to determine whether this difference in the sample mean, the $665, is in fact large enough or not. All I would do is I would normalize. So I'm looking to check if the $665 is in fact significantly different from 0, because the null hypothesis being true as an equality. Remember, all hypothesis testing starts off with the assumption that the null is true as an equality. In this case, if the null is true as an equality, then mu n minus mu l would be strictly equal to 0, which is the middle of the t-distribution here, you can see. Okay, so what I'm really checking is this difference in the sample means that I got, namely the $665. Is it really all that different from 0, or did it simply occur by chance? And the way I do that is simply normalize it. Minus 665 minus 0 divided by 344. So this ends up being, let's see what number we get. This would be minus 665 divided by 344, and that's 1.93. So the physical interpretation is this difference of minus $665 between the new bumper and the low bumper is 1.93 standard deviations below the mean. Is that large enough? Whether it is large enough or not depends on how much risk I'm willing to assume, and the risk I'm willing to assume is 5%. Okay, so let's compute the probability that I would get a sample statistic at least as extreme as minus 665 if the null were true as an equality. That's pretty much a mouthful, but in terms of probability, what this means is I'm looking to compute the probability of t less than minus 1.93. That's the yellow shaded area that you see on the left hand side of the t distribution. This is what I'm about to compute. Okay, so you know that in order to do that, the built-in Excel function that I would have to use is the t distribution equal to t dist, and I have to give it an input of 1.93. Notice I did not put minus 1.93 because t dist only works with positive values of t, and I know that the area to the left of minus 1.93 is the same as the area to the right of plus 1.93. Degrees of freedom is 16 that we just saw and that we just computed above, and this, okay, so I entered too few arguments. Of course, I want one tail. I want the area just on the right hand side. So I want one tail. So I end up with 0.035. So numerically, this is 3.5%. Physical interpretation of this 0.035 is the following. That is, if the null were true as an equality, there is only a 3.5% chance that I would be seeing a sample statistic of minus $665 or less. Okay? So since I'm willing to accept a 5% chance of making the wrong call, this 3.5% is below my threshold. So in terms of pure arithmetic, what this means is p is less than alpha. This is the p-value. The p-value is simply the probability of obtaining a sample statistic at least as extreme as the one you got, provided the null is true as an equality. All hypothesis testing starts with that assumption of the null being true as an equality. Since p is less than alpha, I would end up rejecting the null. So my final conclusion is the following, that if I'm willing to accept a 5% chance of making a type 1 error, the wrong call, then I will conclude that yes, indeed, the new bumper does reduce the average damage compared to the old bumper. Now notice that if I was willing to accept only a 1% chance of making the wrong call, in other words, if alpha was 0.01, was 1%, which is the other common level of significance that's used, then I would not be able to reject the null. So if I want to be that sure of not making the wrong call, if I'm only willing to accept a 1% chance of rejecting the null when in fact it's true, then based on the evidence that I have, I don't meet that threshold. There's a 3.5% chance that I would be seeing what I'm seeing in the sample purely by chance. All right, and that maybe I can get better results by increasing my sample size, look at more cars with new bumpers, more cars with old bumpers. But with the data that I have here, the sample sizes that I have here, I would not be able to reject the null at the 1% level of significance. But I would be able to reject the null at a 5% level of significance, which may be good enough for our purposes here. Okay, so the final conclusion is at the 5% level of significance, based on the data that I see in the sample, I would conclude that yes, the new bumpers do in fact significantly reduce damage compared to the old ones.